So our last skill in Learning Unit 6, which is on thermochemistry, is about delta HF, which is delta H of formation, so a special kind of delta H, and then using values that are tabulated in a reference table that we're going to call Appendix B. B as in boy. And so just highlighting and reviewing some of the places that we've been, we learned about in our second learning unit skill on calorimetry and specific heat capacity. We learned that delta H can be determined experimentally using calorimetry. We can measure the heat given off by a system as a proxy measured by temperature changes through a substance, and we can use that to determine the enthalpy for a system. And in lab, you guys practice that, right, with using your coffee cup calorimeters. Our last skill taught us that, you know what, we can also figure out delta H another way. We can use Hess's law. And so maybe we don't have the delta H for the reaction that we want, but we have delta H's for other reactions that we can manipulate and sum together so that the net sum of those reactions is going to give us the delta H for the equation that we're interested in. So that was skill 6.3 there. So where we're moving on to now in our last skill here is another empirical method for determining delta H. And this is going to be using sort of Hess's law type strategies, but we're going to be using what we call delta H values that are from Appendix B. And we're going to be using an equation here that I know looks a little bit scary. We're going to break it apart on our next slide and talk about what this is. But this is really just a way to measure the costs and the gains or the benefits from doing sort of this theoretical mental exercise, if you will, here. So see if this makes sense here. The reaction that we're interested in is taking some set of reactants in an initial state and converting them to some set of products in a final state. So we'd like to find out what is the energy change for that process in terms of heat given off, in this case for an exothermic reaction. That's our enthalpy. So what we can do is sort of a mental exercise. We can say, let me imagine taking all of these reactants and decomposing them to their pure elements. And then I'm going to imagine recombining all of those elements into my products. And I want to make sure to highlight, this is not anything that happens in real life. This is not what happens in this experiment. But what we're doing is we're sort of walking around the block using information that we have from a reference table to get to the final destination that we're interested in. So it's almost like we've got a detour here. We can't take this walk. We don't have either the experimental way of doing this reaction. We don't have the Hess's law that we can kind of have existing reactions that we have. So we can do a special thing, which is say, let's just take all of my reactants and imagine breaking apart all of those substances into their individual elements. Imagine this being like a Lego set, and you just break everything apart to all the individual Lego pieces, and then you recombine them. Now, Appendix B allows us to figure out what are these different delta H's. Okay, so I'm going to show you through an example problem how this works. But remember that this is sort of a theoretical exercise that we're imagining doing this process. And we're going to look up on a reference table how to use these tables and how we get these values. So I want to highlight here. This equation I know looks scary, but don't worry about it. This is what we're interested in. We're interested in the delta H of our reaction. So what we can do is we can take the reaction that we have, and we can look at the products that we have, and then we can look at the reactants that we have. And we're going to look up those, we're going to look up some values for those reactants and products, and so that's what these delta H values are, is we're going to be looking up these delta H values for these guys. We're going to look them up on this table. And importantly, we need to make sure that we scale these by coefficients. So let me highlight this here. These values that we're going to have here are going to be coefficients from our reaction. And this is always one of these skills that until you see it in practice, it kind of is a little bit confusing. And this equation I know just looks scary. It's got like Greek letters and all kinds of stuff. We're going to do an example problem and it should make sense. But before I do that, I want to make sure to highlight what these delta HF things are. And one of the skills I do need you to know how to do that's sort of embedded in here is how you write a standard enthalpy of formation equation. So I've got 3 examples here just to highlight. When we're writing a standard enthalpy of equation, or standard enthalpy of formation equation, this is how we define it. It is the enthalpy change for the formation of 1 mole of a substance from the elements. Okay, so I'm going to go through 3 examples here. Let's talk about methane. If we wanted to write a standard enthalpy of formation equation for methane, methane is CH4. Remember in our little breaking everything apart in our Lego analogy, we need to break this apart into carbon building blocks and hydrogen building blocks. So we need to know how those guys are found in their elemental state. So we need to know that carbon is found as graphite, and hydrogen is found as hydrogen gas. So a little bit of this is going to require that you know how these are found in their elemental forms. I'm going to give you a little cheater's way to kind of know that using Appendix B in just a minute. But what we need to have now is we need to write an equation that's going to form 1 mole of substance. So notice that this is 1 mole of this. So to have a balanced equation, we might have fractions or non-standard values on our left side. It's always going to be 1 on the right. Okay, make sure you know that. What we can see now is if we look at the value that's given for methane, this guy right here, we can see that's the guy. So this is what we get off of the table. The delta H of formation for methane is going to be minus 74.9. Okay, so 2 things to know here, right? If you have to look up the delta HF for methane, you're going to, and this is kind of like a little mini version of Appendix B, just some values. You're going to look this up on the table. You're going to need to make sure to look up the H column. There's other columns that are there. We haven't yet gotten to those yet. You're going to use the H column, and you're going to find this number. Okay, we're going to go through an example problem in just a second to highlight that. But the other sort of embedded skill here is just knowing how to write a standard enthalpy of equation or formation equation. That's a mouthful. Standard enthalpy of formation equation. All right, so let's go through 2 more examples here a little bit more quickly. So now we're going to be talking about sodium chloride. Okay, that means we need to have sodium Lego pieces and chlorine Lego pieces. So we have to write those as they appear in their elemental forms. So we're going to have sodium as a solid metal, and then chlorine as chlorine gas. Now, I wanted to highlight, if you don't know how something exists kind of in its elemental form, we're going to see over here, so we've got sodium, anything that appears as a 0 here. So these appendices are going to basically have each element, and when you want to find how something exists in its elemental form, it's going to have a delta HF of 0. So that's how you'll know what that looks like in its elemental form. So that's like a little cheater's trick. Just like your periodic table can be a great cheat sheet, your Appendix B can be a great cheat sheet for how you find things in its elemental form. All right, so looking again, sodium chloride here, if we look up sodium chloride here, we're going to have that minus 411.1 kilojoules. One of the things that you'll notice here is most often these values are going to be negative, okay? One more example here, and we're going to highlight an important thing to think about with this example here. When we have, this is methanol, okay? So I can see here's methanol here, minus 238.6. So let's find the important pieces. The Lego bricks that we use to make methanol are carbon, hydrogen, and oxygen. So that's how we're going to find these guys here. Carbon, hydrogen, and oxygen gas. So again, we can write this balanced kind of equation here having these fractions. So we're going to see that these fractions are here. So not necessarily inherent with one of these examples, but I just want to point out, we'll point it out here with water. Notice that water appears twice here, and that's because water can exist in 2 phases as we find it on this table. We've got liquid and we've got gaseous water. So you have to make sure that you grab the right phase of something. And as you're looking at Appendix B is bigger than this because it also has a column that has a G and a column that has an S. We don't want to grab information from those columns, so make sure you're grabbing only from the H column. We're going to learn about G and S later, but not here. All right, so let's go through one example. And I encourage you, if you want, Appendix B is posted under our Resources tab on Blackboard. If you kind of want to go and take a look at that so you can see where I get these numbers, I'm going to give you a strategy for how I like to solve these problems. And it kind of helps keep track and organize all of this information. So first thing you have to make sure you have is a balanced chemical equation. If your equation isn't balanced, this whole process doesn't work. Balanced chemical equation is key. All right, so I've already started here with a balanced chemical equation. So what I'm going to do is I'm just going to look up on Appendix B what these values are. So I'm going to find titanium tetrachloride here. I'm going to find titanium dioxide. I'm going to find all of these things here. So I should say this is, I named that wrong. This is titanium 4 chloride here. It's an ionic compound. So when we have these, I'm going to look them up on our table here. So let me write down the values that I get, and if you want to pause it and see if you can find these same values on your Appendix B. And right now I am just writing down exactly what Appendix B says. So these are from Appendix B as is. Okay? So now one of the things we're going to do, and I know this equation looks scary, but don't worry about it. Our delta H for our reaction is going to be equal to a sum, and we're going to use products minus reactants. Just like we had final minus initial, finals minus initial, we had that in our head. This is an equation that will be provided for you, but we need to make sure when we implement it, we remember that it's products minus reactants. So I'm going to take, and this M is going to stand for coefficients. You're going to see how this is going to come into play in just a second here, times delta H for any of my products minus the sum of the delta H of formation for any of my reactant species. So highlighting here, these represent coefficients. So coefficients for my products are going to be a 1 and a 4. Coefficients for my reactants are going to be a 1 and a 2. So I have to make sure that I use those values. So what we're going to really be thinking about here, and I should have highlighted this over here. Let me slip back just here for a second. Remember I talked to this being about sort of like a cost and a gain sort of analysis. These things right here, everything that we go uphill, we can think of this as sort of being our costs. So let me just kind of write that on here. These guys represent our costs. We're going to have to put energy in to splitting those Lego pieces apart. Anytime we go downhill in energy, this is going to be a gain. Okay, so when we're doing kind of a cost-benefit analysis here, for the overall process, we have to take and we have to consider our products, which again, we're going to be gaining from those, and then we're going to be subtracting our costs. All right, so I'm going to go through and I'm going to put all of these pieces together here. So this really represents, I'm going to put these in big brackets here. I need to take into account the number of each piece that I have, so it's 4 times minus 92.31. I'm going to highlight here. I should have done this before. The units for these are kilojoules per mole. And that's why we need to scale these by the coefficient, because they tell us how many moles of something that we have. So this is really 4 moles of HCl times minus 92.31 kilojoules for every 1 mole we have. So that's why it's scaled up by a factor of 4. So those are going to cancel. I'm not going to keep writing all of those units just because this can get really cumbersome, kind of writing all of this. So that's for our HCl. And then for our titanium dioxide, we only have 1, so I'm not going to worry about that from a mathematical standpoint. And then it's minus 944. So all of these, again, are going to have units of kilojoules per mole when we multiply them by the number of moles we have from the coefficient from our balanced chemical equation. That was a mouthful, right? We're going to end up with units of kilojoules. So this was our titanium dioxide. You don't need to have that down there, but I want to make sure you know where that is. So I am summing, that's what this really means. I'm summing the scaled up version of the delta H values for any of my products. And now I'm going to subtract, and I'm going to do the same thing here for the summed up values of any of my reactants. So I'm going to have 2 times minus 241.826 for my water. So that's for water. And now remember, I'm summing all of these up. So now it's 1 times minus 804.2 for my titanium 4 chloride. Okay, so I have all of these things. This is almost like when you're, balancing your checkbook or something like that. There's all of these pieces that sort of have to come together. I'm going to do all this math. If it helps for you to kind of figure out, remembering these are our gains. These are our costs. When we have all of these that are kind of coming together here, if you want to kind of figure them out each separately, then you can do that. But at the end of the day, this is all going to be equal to delta H of reaction. Delta H of reaction, when I sum everything up here, is going to be equal to minus 25.388. Now remember, we're doing a lot of addition here. So when we consider significant figures, we have to look at how many things have stuff to the right of the decimal place. There's a lot to the right of the decimal place with this guy. This guy has nothing to the right of the decimal place. So that's going to kind of limit what we'd have here. So truthfully, this would probably be 25, but I'd be okay if you had 25.4, and the units of your answer are going to be kilojoules. Notice they aren't kilojoules per mole. We got rid of that mole when we multiplied by those coefficients. So the units of these are going to be kilojoules. Again, if you rounded this to 25, it's probably better from a significant figure standpoint, but that's how you can use Appendix B to determine delta H of reaction.